How you draw a bell-shaped curve is really your choice. It depends on what you think a lovely bell is. Some people choose to draw them tall and skinny. Some people choose to draw them more gently. It has to really do with the units of measurement that you have chosen along your horizontal axis. So while in a sense there is only really one bell, you can see physically that it looks as though there are many bells depending on how you chose the center and how you chose the spread. And indeed there is a general form of the equation for the normal curve, but not the standard one, the one with a mean mu, that's the Greek m for mean, and SD sigma, that is the Greek S for SD. And that curve looks like this. A bell-shaped curve centered at mu with its points of inflection at mu plus sigma and mu minus sigma, mean plus an SD, mean minus an SD. And you see that I've called it x, not z. This is not in standard units anymore. It has an equation with those same numbers, the square root 2, the pi, the e, and look what you see here. You see your value x minus the mean divided by the SD. That's standard units. That was the z that you saw earlier. But now we are writing it in terms of the units of measurement of the variable being x, which could be inches or pounds or degrees Fahrenheit or whatever it is. This goes out from minus infinity to plus infinity, as did the original curve, but as did the original curve, the actual area that is visible, at least on this scale, is on a very limited range compared to the whole real line. What do we know about this curve? We know its total area is 1. We know its balance point is mu, we can see that. And the points of inflection are at mu plus and minus sigma. And if you convert to standard units, then you've got the standard curve that we've been looking at in the previous segment. If we walk away from the mu's and sigmas for a second and look at what happens when we are working with a physical variable, let's examine this statement, which I've put in quotes. A distribution of heights follows the normal curve. Here I say this is an imaginary ideal because if I have a list of heights and I draw its histogram, that histogram is going to have bars. It is going to be jaggedy. But I am assuming here that my heights have been measured to such precision that they are perfectly continuous and follow this lovely smooth curve with a mean that I have specified and an SD that I have specified, 67 plus or minus 3, and that curve looks like this. Centered at 67 as you'd expect, and now look at where the SD is. You can see the SD on a normal curve in a way you cannot see it on any other curve. 67 plus an SD is a point of inflection, minus SD is a point of inflection. So if you are told the mean and the SD of the normal curve, you can put down your horizontal scale in a manner that shows what the SD is. The SD is the distance between the center and a point of inflection. What do we know about this curve? Well, we know that its total area is 1. We know that it balances at 67. We know that its points of inflection are at 67 plus or minus 3. And we know that these numbers, if you convert them to standard units, then 67 is going to become 0, 70 is going to become 1, and you're going to have your old friend, the standard normal curve. And that's the idea that we're going to use to find areas under this curve. Why do we want areas under this curve? Well, if you want to figure out what percent of heights are in a certain range, for example, what percent are in the range 64 to 70, well, that's 1 SD above and below. On the standard unit scale, that's the area between minus 1 and plus 1, and we said that was roughly 68%. If we have any other range down here, then what we have to do is one little calculation to see where that range is on the standard unit scale. So let's do an example of that. You've got our old friend, the distribution of heights, and the question is, what percent are between 63 and 67? Again, I am assuming that these heights follow the normal curve exactly, which is an imaginary world, but I'll stick with it for now. So I need to find an area under the normal curve, the only normal curve I have whose areas that I know is the standard normal curve. And so if I'm going to use that, I need to convert to standard units. 63 in standard units, 63 minus the mean divided by the SD is negative 1.33. 67 inches is just 0. It is the mean. I don't have to do a calculation. So I have translated my question in terms of the standard curve. And the question is now, under the standard normal curve, what percent is in the range negative 1.33 and 0? So how do I find that? Well, yeah, I go to my applet. And my applet says that if I put the lower endpoint as minus 1.33, which is what I want, and the upper at 0, then the area in between those two under the curve is 40.82%. The applet says the area is 40.82%. What do I do to that? Nothing. I'm done. The question stated with inches as the variable is the same as the question that we just answered with standard units as the variable, and so your answer is 40.82%. 40.82% of the heights are between 63 and 67. So if you are trying to find a percent under a normal curve, convert your endpoints to standard units and use your applet. We can use the same idea backwards to find percentiles. So we've got our same distribution of heights, and the question is now, what is the 40th percentile of the heights? I'm looking at that and I know that my answer is going to be less than 67 inches. 67 inches in the normal curve is the 50th percentile. So what is it going to be? How far below it is it going to be? Well, let's find the 40th percentile of the standard curve by going to the applet. And the applet says that the 40th percentile of the standard curve is negative 0.253. No surprise that it's negative. It's below the center. It's the 40th percentile. 0 is the 50th percentile. So the applet says that the 40th percentile of the standard curve is negative 0.253, and that is my answer. I am done. Well, except I'm in the wrong units. I'm in standard units. I don't want standard units as my answer. I want a height. I want a height in inches. So what do? I convert these standard units to a height. I know how to do that. The height that I want is minus 0.253 standard deviations above the average, and that is 66 and a bit inches. Just below 67, as we had expected. And so what you know now is to use your standard normal applet to find areas and percentiles under any normal curve at all.